Today we shall look into durability of concrete. So far we have looked into strength, and then now today we will look into some aspects of durability of concrete, degradation processes and attacks on concrete. So, in general outline of our discussion will be what we understand by durability and service life. Then we shall look into role of maintenance and look into some of the degradation processes. So, let us try to define durability. You see, one thing so far we have understood is that concrete structure can remain stable, and strength is a factor which actually decides about whether it will be safe and stable against horizontal, against horizontal and vertical loading, gravity loading and horizontal loading. But this is one issue, as something strong can also be attacked by various kind of aggressive agents present in the environment. So, durability relates to these issues, right. So, deterioration can take place because of some of the chemical attack from the environment. The concrete structure shall survive and serve its function during the period of intended design life. You see, we will try to define life of the concrete. First of all, we define intended design life. If you remember, we talked about life of the structures, that it's the life of the structure which it should act, for which it should function. Now, intended design life is during the time of design, whatever is the life you conceive, that is called intended design life. So, you take the load that would come during that period of time, the maximum load or possible most probable maximum load with certain amount of risk that will come once during that period of time, and you design for that to sustain such kind of load. But this is the intended design life of the structure. There can be several other ways of defining life. Service life is normally defined with respect to elements. Now, we can define the service life in such a manner that it should serve its functions during that period of time satisfactorily. So, in any case, as far as structure is concerned, it shall survive, should remain stable and serve its function during period of intended design life. And of course, we will be doing some maintenance during that period of time. It is not like that you built a structure, whether it is a building or let us say a bridge, that you built it and it remains forever without any maintenance. You have to do certain maintenance, and when you do maintenance, the structure should serve its function during the period of intended design life. Satisfactorily it should do that job. Let us formally define the durability. Durability of structure, component or any material, any product, etc., can be defined as its capability to maintain a minimum performance level over the specified time when exposed to degradation environment. So, what is it actually? Durability is related to environmental degradation. When you expose a concrete structure to environment, it would actually be attacked by various aggressive agent in the environment, and this would mean it has to survive such attack during the intended design life period. So, durability is related to its capability to survive the environmental degradation and maintains a minimum performance level during the specified time. That is what we call it durability, right. There is an analogy with human being. You see, a person can be very strong, young person can be very strong, but still can be attacked by viruses or can fall sick. So, the remaining healthy is the part related to durability. Strong person can also fall sick. So, that is, or be attacked by virus or bacteria or whatever it is. So, we are talking here, when we talk of durability, we talk of those kind of action from the aggressive environmental agent, right. So, let us see now What are performance? I have been just talking about various performances. Now, performances are the measures of fulfillment of functions. For example, a structure is supposed to carry load, allow possibly, let us say if it is a bridge, as I mentioned sometime earlier, a bridge is supposed to allow traffic to pass over it safely and of course remain standing during the period during the period of its exposure or during the period of its intended design life. So, performances are the measures of fulfillment of its functions. So, these functions it should bridge should perform this function of carrying the traffic or allowing the traffic to pass through it. Now, this function how it performs, how it fulfill this function is defined in terms of performance parameters. So, performance are the measures, they are the measures by which you actually define how it fulfills its functions, right. And this performance can vary with time. For example, load carrying capacity of the bridge may get reduced or something like that due to environmental exposure and action of the aggressive agent, deterioration of its material and components. So, performance can vary, where there can be various other performances. For example, performance may be defined in terms of not only carrying simply the traffic, but there should be crack. So, we can define the performances that visually also it should look healthy or aesthetically it should look pleasant. So, these are also some other kind of performances. So, these performances can vary with time. For example, at the beginning it may not be showing any crack, any signs of any kind of distress, but with time it might show some signs of distress and which may not be acceptable. So, performances varies with time and degradation is basically gradual decrease of performance with time. So, these are some of the definitions with reference to durability, right. So, we now understand what is performance, we also understand performance varies with time and what is durability. In this context, we would like to define service life of elements. Now, let us first just look at it philosophically. We think that buildings or structural materials, if we once produce, they are all maintenance free. Well, they are very unlikely to be maintenance free, because let us say cement, we produce it at the expense of energy, we heat up the raw material and actually embodying some energy into this material. So, it is not its stable condition. Stable condition would be when it has dissipated all its energy and no chance of dissipating any further energy. Actually, we raise the chemical potential by heating this up and it would like to dissipate that energy as and when it gets a chance. So, cement reacts with water, dissipating some of its energy, which is, we know that reaction is exothermic. So, all the materials that we produce at the expense of energy would like to dissipate them and therefore, they will deteriorate. So, therefore, concrete cannot be maintenance free. In concrete, cement we are using, some of its of course locked up energy is dissipated during the hydration reaction, but still there will be some amount of energy remaining. So, altogether it would like to come to a stable state by dissipating all its energy. So, given a chance, it would like to react with environmental agents, those are present, and get degraded. So, that is why concrete cannot be maintenance free. We know steel is not, steel readily forms oxide and rusts, so is concrete. So, therefore, one has to maintain them, one has to see that how you tackle this sort of problem, that it will have a tendency to react or degrade. But then if you know this degradation behavior, there is no problem, because you can design keeping this in mind. So, it has to be by design, not by default. You can, tendency of degradation may not be controlled, but rate can be controlled by various means. An analogy is again is shown quite often, that you can lift up a body up. Now, if you just release it, keep it in the air, it will come down. If you something like this, this is your ground atom, you raise a body and lift it up. Now, if you just leave it in the air, it will come down straight away, it will have a direct fall. If you put it in a slope, well, it will come down, but come down at a much slower rate. and if you just put a flat surface, you built a flat surface and just hold it there, it will never come down, because although it has tendency in all cases are same to come down, but rates are different. So, in the first case when there was no support, the rate was maximum, quickly it will have come down. When there is a slope, it will come down slowly, and when you put a platform below it, actually it will never come. So, rate can be controlled, and although we cannot rate can be controlled, although we cannot control the rate can be controlled, although we cannot control the rate can be controlled, although we cannot control the potential or the tendency to degrade. Anyway, all that is there. So, concrete degrades with time, and therefore, one can talk in terms of what is called service life of concrete element. So, we are talking in terms of service life of concrete element. So, the initially the degradation level is 0, and then it degrades gradually like this and reaches a level which is not acceptable to us. When it reaches such level, then it is not acceptable to us, we call it service life. Service life is that life usually for concrete elements, not for the whole building, concrete elements. We are talking of service life of concrete elements, and remember, once an element reaches its serviceability limit and in fact its service life is over, whole structure is unlikely to collapse. What you got to do is, you got to actually repair. You repair it and maintain it properly, then of course, it will be back to the the structure will still remain safe. Besides that, structure has got enough built in redundancy, so that if one element is one column even in a building, let us say supported on or a slab supported on 4 columns, you cut one column, unless it is very critical structurally, the other 3 columns will share the load, and so some degradation in one column is not going to make the building to fail, but it has got its implication on maintenance. Well, in extreme cases, when it is unattended, it can fail also. It is not that one can sit pretty, it can fail also if unattended, but with proper maintenance many of the durability problems can be taken care of, but it has got its implication on economics. We will look into that. So, serviceability limit or service life we define with respect to an element, let us say a beam, a column or slab or something of that kind, when the it would depend upon of course the case, specific case of degradation process also. So, when initially it is in good condition, and when it reaches a defined serviceability limit, for example, it could be simply that appearance of visible cracks and so on. So, it will depend upon the degradation process, and when it reaches the serviceability limit, this time we call as a service life of the element. So, this has got the relevance in durability, and one would like to design an element for appropriate service life, right. One would like to design service life, and if we see what is its role in maintenance, this diagram shows the role of service life in maintenance. You see, you can see that this is initially there was no degradation T0 period, and after that possibly degradation start, and then it would have reached the serviceability limit. But one might take a decision that, well, generally when it is normally accepted much before the serviceability limit, you might do maintenance and bring it back to the original condition. Then again it will deteriorate, and then you have periodic maintenance. So, when you have degradation or deterioration problem of concrete structures, you might think in terms of doing it repetitively, maintaining it repetitively, doing some repair and rehabilitation repetitively till the intended design life. So, series of repair, this time you do a repair, this time you do a repair, this time and this. This could be one of the managerial decision depending upon economics and what is called life cycle cost. That is, every time you do a maintenance, a cost is incurred, and this cost can be compared through what is called life cycle cost analysis. But as another managerial decision or another option could be, well, you repair it in such a manner that it reaches, it follows that path, instead of following this path, it follows this path and then lasts for last for intended design life. So, this is service life is related to maintenance policy, and durability is also related to maintenance policy. So, one can take policy decision based on durability quality of the material. You select a material which will last for very long, right in the beginning it will simply last, simply last during this period of time, or you can have another material then which will last for certain period of time, it will deteriorate, bring it back to original condition, and so on and so forth. But in both the cases cost should differ. In one case the initial cost would be high, in the case where you have many repetition of the repair, the initial cost would be low, but maintenance cost would be higher, repair cost would be higher. So, one might take an economic decision based on what is called life cycle cost analysis. Well, at the moment that economics is not our business, we are trying to look into the durability problems of concrete, how durability and how it is relevant, but this is the overall relevance of durability in maintenance policy. Okay. Let us see what are the degradation process and chemical attacks that takes place in concrete. If we look at the degradation processes, we will discuss all of them one by one. Sulphate attack, then there is seawater attack and acid attack. So, concrete is attacked by sulphate, we will see that in detail, seawater attacks and acid also attacks. Then carbonation and chloride ingress, these are not really directly they do not affect the concrete, but they affect the reinforcement, and it is a very major issue. They affect the reinforcement, and reinforcement corrodes. As I have mentioned earlier, reinforcement normally we use are steel, the alloy of iron carbon, and steel in various forms. Now, this steel is again produced with expense of energy. Iron in nature is available as iron oxide, iron pyrite, sulphide or oxide forms, magnetite, hematite, whatever they are, the ores are. Now, this therefore, iron Fe in its Fe state is never available in nature. Although in steel also it is in some combined form, maybe in FeC or some other combined form, but this Fe has a high tendency to react with oxygen, forming oxides or hydroxides, because again we have produced from the ore, we have produced the steel with expense of energy. So, this will have a tendency to actually go back to a stable state, and therefore, iron in steel oxidizes or gets corroded. So, rebar corrosion, actually carbonation and chloride ingress, although they are not they are not dangerous or they are not really a durability problem for concrete per se, but concrete is rarely used as plain concrete. Most of the time we use them as reinforced concrete or pre-stressed concrete, and in either case the common reinforcing or pre-stressing material is steel. So, this steel can corrode. So, this is another durability problem, and we will look into this also. Then there are other durability problem called alkali aggregate reaction and attack of frost action in concrete. So, this is a physical one, others are chemical. Some of those deterioration processes are chemical, some of those are physical, but it all takes place due to its exposure to the environment and aggressive agents coming from the environment in some form or other. So, physical is this, there can be some other physical also, and that is how that is the degradation process. So, we will discuss the first two today, and the alkali aggregate and frost reaction we will discuss in the next lecture. So, let us look at the sulphate attack first, but before that let us understand one thing, that all of this degradation process, whether physical or chemical, generally chemical ones involve presence of moisture and also involves ingress of aggressive chemicals and moisture from outside, and they can be modeled through various diffusion processes. But then at the moment we are not interested in the models, but what I want to actually highlight is the fact that it is the moisture which is very important, and ingress of aggressive chemicals which is also important. So, two issues are important, the moisture ingress and aggressive chemical. Presence of moisture or water or in vapor form or in liquid form, that is most important. and it has to enter into the concrete. So, we will discuss more onto it later on when we discuss general issues, but let us right now look into chemical attack. Even in case of physical frost action, it is again the water ingress which is important. So, either physical or chemical, the role of moisture is very important in case of due to durability of concrete. Okay. So, let us look into some of those attacks like sulphate attack. If we remember, we added gypsum to cement, in case of during its grinding process, and why? This is because to control the setting, and when we discussed hydration of cement, we said it is the C3A which reacts quickly with gypsum and forms ettringite, a compound ettringite. Therefore, C3A reacts with gypsum, that is calcium sulphate, forming ettringite. Now, this reaction in the soft paste or concrete, in case of before setting plastic concrete, is not a problem at all, because in plastic concrete, if ettringite which occupies more volume than its reactants, that is C3A and gypsum, does not create any problem in plastic concrete, because this expansion can be accommodated by the plastic concrete, because it is in plastic state. So, something is trying to push the material apart, it simply allows that movement, it is plastic. So, paste in its plastic state can accommodate the ettringite reaction, that is C3A reaction with gypsum forming ettringite. But supposing this is happening in a later date, that is when concrete has hardened, cement has hydrated, concrete has hardened into a solid mass, and the C3A inside the concrete, that is the C3A hydrates which is present in concrete, tricalcium aluminate hydrate present in the concrete. Now, it reacts with gypsum or calcium sulphate, forming same ettringite, and wants to ettringite would like to occupy more volume, it will have a tendency to occupy more volume. So, what it would do? It would actually exert pressure onto the concrete. So, gypsum reaction in the plastic concrete, it controls setting, but in the long term it can cause expansive pressure within the concrete and cause cracking. That is what is the essence of sulphate attack. Let us see slightly more the chemical reaction aspect of it. So, sulphate reacts with calcium hydroxide and C3A and forms ettringite and gypsum. You see how it is, let us see, because the statement is something like this: sulphate present, say let us say sodium sulphate, it will react with calcium hydroxide present in the concrete as a result of hydration of cement. We said that C3S and C2S reacts with water, forming CHS gel structure and also calcium hydroxide. So, sodium sulphate reacts with calcium hydroxide, and then this forms calcium sulphate and then sodium hydroxide. So, sodium hydroxide formation takes place and calcium sulphate. So, whether the sulphate is in sodium sulphate form or potassium sulphate form, they will quickly react with calcium hydroxide forming calcium sulphate. Now, this calcium sulphate, you remember this calcium sulphate can be written in cement chemistry abbreviated form as this. This CS bar is nothing but, you remember we said that SO3 can be written as S bar, and therefore, when I write C is nothing but CaO. So, CS bar is nothing but CaO, SO4, CaSO4. CaSO4. So, this is calcium sulphate, the same one, same product calcium sulphate, and this is reacting with tricalcium aluminate hydrate, gives rise to this salt which is called ettringite, C3A dot 3 CS bar, it just get absorbed plus the water which was present and forming calcium hydroxide again. So, this gives rise to ettringite formation. This is ettringite, the volume expanding, which occupies more volume. So, this is ettringite and it can occupy more volume. So, original volumes of the reactants were something like this, now it wants to occupy more volume and you have surrounding material all over the place. So, it will exert pressure onto those surrounding materials and eventually cause cracking of those surrounding material, that is the cement paste, surrounding cement paste. So, eventually it causes cracking of this paste. So, ettringite occupies more volume leading to disruption of concrete, there will be cracking, spalling of concrete will come out. So, that is what is a sulphate attack. So, if the concrete is exposed to sulphate environment, this can result in this sort of so say soil containing sodium sulphate or potassium sulphate, this can result in sulphate attack. There can be several other situations where sulphate are present and sulphate attack could be there. Now, let us look into another case of sulphate, one specific sulphate, that is magnesium sulphate. Now, magnesium sulphate is the one, this reacts with calcium hydroxide forming calcium sulphate and magnesium hydroxide. So, calcium hydroxide concentration reduces, and it forms same gypsum, which will form then again ettringites, which will form ettringites, right. Calcium sulphates would lead to formation of ettringites, and magnesium hydroxide which is present, it causes some other kind of problem. The CHS gel that we have talked about, that is the cementing material in cement hydrate, that is unstable in the environment of magnesium hydroxide. In calcium hydroxide environment it is okay, it is stable, but in magnesium hydroxide environment it is unstable, and it so happens when you have magnesium sulphate present, it converts all the calcium hydroxide to magnesium hydroxide. So, this CHS tend to decompose in magnesium hydroxide environment, resulting in formation of magnesium silicate hydrate in the long run, So, this is important. This is unstable in magnesium hydroxide environment, and finally, this is formed, and this has got no cementing property. So, cement in presence of magnesium hydroxide, the cement hydrates, not only ettringite formation can take place, but at the same time it can also destruct, it can destroy the CHS structure, therefore, the bonding properties of the cement will be lost. So, it will be simply even more dangerous, magnesium sulphate is more dangerous than others. Now, what are the symptoms? You actually see white crystals of gypsum when such sulphate attack takes place, and you will have obviously cracking, spalling, etc. So, sulphate attack finally results in cracking and spalling of concrete, and there is formation of gypsum powder. So, white gypsum crystalline powder you will see. So, white powder of gypsum together with powder formation, if you scratch it, for example, scratching the surface, if this is your surface and you scratch it, you will find lot of materials comes out. This is the concrete surface, let us say, this is the concrete surface, and the column vertical surface, you scratch it a little bit, you will find dust, fine powders comes out. So, this is, and then white crystals of calcium hydroxide is usually present. So, this is the symptom of sulphate attack. It can happen in many places. How to protect? Obviously, lower water cement ratio improves the sulphate resistance, because I said that penetration is required. The water has to penetrate because reaction takes place in solution form. The sodium sulphate in solution form has to enter into the concrete. So, if you have lower water cement ratio, you will have less porosity, and therefore, it can improve the sulphate resistance. So, that is the primary protection measure, but something more important, which causes reaction, which reacts with the sulphate? It is the C3A. So, therefore, C3A cement, high C3A cement would have higher sulphate attack tendency to sulphate attack, less resistance against sulphate attack, but low C3A cement will show better resistance to sulphate attack, and blended cement improves sulphate resistance, right. So, blended cements means we said that blast furnace slag cement, and also any blended cement, because it will reduce down the C3A, lower down the C3A by sort of dilution effect, it will reduce down the C3A content, because if you are using some percentage of blending material, blending other materials, a pozzolana or similar sort of thing, obviously OPC content is reducing, proportionally C3 will reduce. Some of them make it impermeable, very impermeable, relatively more impervious structure of the cement hydrate, as we have observed earlier in our earlier discussion with respect to hydration of cement. Therefore, it improves the sulphate resistance. It improves the sulphate resistance. Let us see to the next attack, seawater attack. Now, what does seawater contain? Seawater contain sulphates as well as chlorides. So, you have calcium sulphate, sodium sulphate present in seawater, and in addition you have got sodium chloride, etc. So, chloride and sulphate both are present. So, now same sulphate means it will form same ettringite, and of course, calcium sulphate formation will take place, but the expansion and cracking it does not result. The reason is ettringite and gypsums are soluble, they are soluble gypsum, these are soluble in chloride solution, thus no expansion and cracking, Since they are soluble, ettringite is soluble, so the moment it is formed, it is it's more soluble in chloride solution, seawater. So, therefore, there is no expansion and cracking, it gets dissolved, right. Okay. But what happens? This will result in leaching, this get dissolved, ettringite which is formed, it is dissolved, calcium sulphate which is formed, it will get dissolved, therefore, this will get leached out, this will get dissolved and taken away by the seawater. So, leaching can take place and it can be severe. So, dissolution of ettringite and gypsum cause severe leaching. Now, leaching causes problem because more seawater can penetrate, and therefore, it is a kind of nonlinear effect. Leaching, further seawater will penetrate, more leaching, and so on and so forth. Where there is a wetting and drying, the zone where wetting and drying takes place, crystallization of salts can take place in the pores that is formed, because now there has been sufficient leaching and a lot of pores, and originally if there are pores, there will be now more pores, and if it is in the wetting and drying zone, that is between the highest water level and the lowest tidal water level in sea, then what will happen? Some of those salt will get inside the pore and the water will evaporate, and crystallization of salt can actually exert pressure onto the concrete structure. So, this may cause expansion, crystallization of the salts within the pore may cause expansion and therefore cracking. This happens between in zone where wetting and drying takes place, and not of course completely submerged situation. But more importantly, reinforcement corrosion can take place, because we said the chloride do not attack the concrete per se, but chloride actually initiates corrosion process of steel in concrete. So, if the concrete become porous, more chloride can penetrate and reach to the river level, and it can initiate river corrosion process. So, initiation of river corrosion is possible, and that is more dangerous, right. So, this is important. Sulphate issues we have discussed, but river corrosion will come to this a little bit later. How can you improve resistance against seawater attack? Blended cement, sulphate resisting cement really do not help much here, because sulphate resisting cement can prevent the sulphate attack against, let us say, sulphate present in seawater, but it has another side effect. You see, it does not help against chloride ingress, rather it reduces what is known as chloride binding capacity of the concrete, because it is C3A which can bind some of the chloride chemically and would not allow reaction of the chloride to proceed, initiating reinforcement corrosion. So, when you reduce down the C3A in sulphate resisting cement, this is not very helpful against chloride attack. chloride ingress or river corrosion due to chloride. So, therefore, sulphate resisting cement is not a good solution as far as sea water is concerned. So, sea water attack it can better resisted, it can be better resisted by Portland slag cement. This performs best in sea water, and obviously lower water cement ratio and quality concrete is the other measures of protection. In fact, we will see this time and again, lower water cement ratio and quality concrete is the most important feature as far as durability is concerned. So, this issue we will discuss in more detail sometime later on. Let us see acid attack. Portland cement is alkaline and therefore will be attacked by acids, because any alkali material is attacked by acids. So, sulfur dioxide, carbon dioxide and other fumes in presence of moisture attack concrete. This is the case in industrial situation, because sulfur dioxide and carbon dioxide, they can react with water forming sulfurous acid or carbonic, and then of course, sulfuric acid when it get oxidized. Carbon dioxide can react with water forming carbonic acid, etc., and they can attack the alkaline material in concrete, namely calcium hydroxide, sodium hydroxide, etc., sodium potassium hydroxides, and in industrial situation many other fumes are there, acidic fumes which can attack the concrete. Below pH 6.5 attack usually initiates and is severe in below pH 4.5. Now, this results in what? This results in actually removal of lot of material from the concrete, removal of, because it would attack and those materials will be leaching sort of action will be seen, a lot of material will be taken out. One special case is H2S in the sewer lines. This, when it is dissolved in moisture, films in sewers and then oxidized, form sulfuric acid. So, in sewers at the point of where low water level to high water level, you can have again attack due to sulfuric acid, which forms due to dissolution of H2S in the moisture film and then further oxidization of the product. This attacks, what does it do? It dissolves and removes part of the cement hydrates, normally leaves weak mass. So, that is what it is, because it would it would form, the acids would actually attack the alkaline material in concrete and remove those salts, those have been formed and leaves finally weak mass. So, that is the result of acid attack. How will you prevent? Well, reduction of calcium hydroxide, if in some cases by treatment with sodium silicate helps in formation of called silicate water glass sodium silicate. So, treatment by sodium silicate helps in formation of calcium silicate and reduction of calcium hydroxide. So, you can actually use sodium silicate and form calcium silicate within the pores if required, and that in an acidic environment. If you envisage the concrete is likely to be in an acidic environment, so you treat the concrete with sodium silicate or what is called water glass, and this will actually help in formation of calcium silicate and reduction of calcium hydroxide will be there. But the other solutions should be, obviously, as I said, low water cement ratio is very much there, that would be there, and also quality concrete. Now, all right, this would be the thing. Blended cements, they will be also other important means of protection, as we shall see. But something else you can do, some cases, in specific cases where high acid attack is actually envisaged, where you think that there is possibility of high acid attack environment which is highly acidic, you will have surface treatment, coatings and various kind of surface treatments, maybe coating, pore lining treatment. There are varieties of treatments are available for such surface. You can give some coating or sort of rendering, a thick plaster sort of thing, and there are other kind of surface treatment which one can provide, maybe bituminous, epoxy and such materials, and they can actually provide protection against acid attack. I said blended cement will it will also improve the resistance against acid attack, because pozzolana in the blended cement would consume a good lot of calcium hydroxide. So, thereby acid attack can be reduced, and it also makes impervious. So, this is how we can protect against acid attack. Let us now look to the next phenomena, service life with respect to corrosion, river corrosion, because the next attack is river corrosion. And we define it in a slightly different manner than we have defined earlier for general definition of service life. Here we will see that we define service life in two segments. First is a relatively less slope portion, then a rapid slope portion. Now, normally cover concrete is supposed to provide protection to the reinforcement bar by not exposing it to the environment. Therefore, bare steel, if you put it into the environment, moist, especially moist and oxygen available environment where moisture and oxygen is available, aqueous corrosion will proceed. But then cover concrete in reinforced concrete is supposed to provide protection to the reinforcement bar. Now, if the cover concrete itself in a way deteriorates or allows something to come in such that the protection it was providing is not available anymore, then corrosion will start. So, that is why there are two phases. First phase, actually concrete itself is degrading in the sense that the protection it was able to provide to the reinforcement, that capability is lost. And once that is lost, actual corrosion starts, which although could be possibly sort of varying like that, varying like this, but we approximate it to the linear line. So, this is one sort of notional understanding. So, service life with respect to corrosion has got two phases. The first phase where concrete protection provided by concrete will be lost, that we call as depassivation period, we call it depassivation time, this is we call as depassivation time. Then second period we call as corrosion time. During that period, since the protection is lost, now the corrosion will start and corrosion will continue. So, corrosion time. So, sum total of service life is a Tp plus TC, Tp plus Tc, both sum total gives us the service life. So, this is what we see is the sum total of these two with respect to corrosion, service life. Now, what is the serviceability limit we define? Serviceability limit is defined as the crack, first visible crack that is observed on the surface of the concrete. So, this line represents appearance of first visible crack, appearance of first visible crack. Now, how does the protection given by concrete is lost? Well, how does first then we should look into how does concrete provides the protection. As I mentioned to you earlier, steel or the iron in steel has a tendency to come to a stable state. So, it will get oxidized, it will have a tendency to oxidize, and this tendency we can't reduce, but what we can reduce? We can reduce down the rate at which it will get oxidized, and this can occur when pH of the concrete is high. This is one issue. Second aspect is this protection is, this protection is provided by formation of some oxides layer over the steel. Now, oxidation we can't stop, but all oxides are again not dangerous or not detrimental from the point of view of its performance. It can still perform even some oxides are formed, so long as the oxides those are formed, iron oxides which are formed over the steel bar do not consume the iron at a very fast rate or does not occupy large volume. So long it occupies less volume, does not occupy large volume compared to the original volume of the steel, it will not exert any pressure, as we shall see later on in one of those slides, the action of rusting. So, when it exerts, the product occupies large volume compared to the original volume of the steel, it will exert pressure to the concrete and cause cracking. But if it does not occupy large volume, in other words, if the density of the product of rusting is nearly same or close to the density of the steel itself, then it is not a problem. This is one issue, and second issue, its rate should be slow. So, iron oxides FeO, Fe2O3, Fe3O4, these oxides form what is known as black rust, and this black rust are not so dangerous because they do not occupy large volume compared to the steel. But if a product like this is formed, or if I may write it in another way as FeOH3, right, FeOH3, this is called red rust. This occupies 3 to 4 times, it occupies 3 to 4 times more volume than the original steel. It is called red rust. These are black rust, this is red rust, black rust. So, these are black rust, these are red rust. So, red rust occupies more volume than the original steel, and this is dangerous, this is not dangerous because it does not occupy more volume than the original steel. So, it does not exert pressure onto the concrete. So, if this is forming, I am not really worried, and this coating, when it is formed, it actually what is known as depassivates the steel, resulting in reduction of the corrosion rate. So, in certain environment, steel remains depassivated. When pH of the concrete is high, concrete surrounding pore solution, concrete pore solution or the material in the pore solution surrounding the steel bar, when its pH is high, then it gets depassivated. In such situation, black rusts are formed, but at lower pH, red rusts are formed. So, high pHs, since black rust is formed, it gets depassivated, but if the pH is brought down by some means, then this it gets passivated when black rust is formed, and if by some means, if pH of the concrete pore solution, pH of let us say water around the steel bar is lowered down, then red rust formation will start. That is we call processes we call as depassivation. Passive film formation, Fe3O4 etc., black rust form a passive film. When it is broken down, we call it depassivation. So, depassivation takes place at lower pHs. Now, concrete normally will be of high pH because calcium hydroxide is there, sodium and potassium hydroxides are also all be there, they maintain a high pH in concrete. But with time, if the carbon dioxide from the atmosphere come and reacts with the calcium hydroxide present in the concrete, forming calcium carbonate, that process leads to reduction in pH, and we know this process is carbonation because we have talked about carbonation in the context of shrinkage and also in the context of non-destructive testing. We will just look at it in more details. This carbonation can reduce down the pH of concrete, and other agents we can actually accelerate the corrosion process or depassivate this, break down the passive film or passive layer of black rust is called chloride, free chloride, water soluble chloride. So, these two agents can actually break down the it can actually lower down the passivity or break down the passivity of concrete and depassivate it, and then corrosion can initiate. Let us see the carbonation process. If we see the carbonation process, carbon dioxide from the atmosphere enters into the concrete, as you can see through this diagram. Carbon dioxide can enter through the concrete. So, carbon dioxide actually diffuses through the air filled pores, and then the chemical reaction with the with the lime, calcium hydroxide present in concrete takes place. Now, where does the lime comes from? It comes from the hydration of cement. We know that C3S and C2S, when it reacts with water, it forms lime. So, this lime reacts with the carbon dioxide of the atmosphere, but this all happens in the presence of water. If there is no water, this reaction will not proceed and forms calcium carbonate, and again water, and this process we call as carbonation. So, this chemical reaction we call as carbonation, and this carbonation results in formation of calcium carbonate, converts calcium hydroxide into calcium carbonate. This is not voluminous, this does not occupy more volume, this does not occupy more volume. So, it does not cause cracking of the concrete, in fact it forms a very hard mass. So, if the carbonation front has reached up to this, it will form a very hard mass up to this. So, carbon dioxide penetrates and surface, first the surface concrete will get carbonated, that means calcium carbonate, calcium hydroxide at the surface will get converted into calcium hydroxide at the surface will get converted into calcium carbonate. Once a layer of calcium carbonate has been formed, carbon dioxide will actually diffuse through that layer of carbon dioxide, and then the reaction will proceed below that layer of calcium carbonate, and carbonation front as we call it, it proceeds within from surface to inside of the concrete, and this is where up to this actually carbonation front has now reached and where this reaction continues. Of course, there are intermediate reactions, because normally there will be a sodium hydroxide reacting with the carbon dioxide forming sodium carbonate, then reacting with etc., but final product is like this. And this causes reduction in pH of the concrete, because it can, when it consumes all the calcium hydroxide present in the concrete or all the alkaline material present in the concrete, pH of the concrete will come down, and this process lowers down the pH, and the passive film which was there, when the pH becomes below 9, the passive film can get actually depassivated. So, pH of the pores initially was around 12.5 in concrete, or even higher 12.7, 12.8, very close to 13, right, and then it comes down, right. So, this through the pores this occurs, actually carbonation occurs. Now, what are essential requirement? Water must be present here, water must be present, presence of water is must, this must be there, because the reaction proceeds in presence of water. Of course, presence of carbon dioxide is must, and carbon dioxide is present in the air. So, presence of both water and air is must. So, therefore, this reaction proceeds when these pores are actually moist pores, there is water at these surfaces, but air is available. Why air is available? Both air, it is not fully saturated. If it is fully saturated, totally wet concrete, then carbonation will not proceed, and if it is partially saturated, then only carbonation can proceed. So, that is the carbonation process. This reduces down the pH. Now, in the next class we shall look into, we shall continue from the process of carbonation to chloride ingress and rebar corrosion. Now, how can we stop this carbonation process? Actually, the permeability of the concrete at the surface is most important. If your concrete is impermeable, then impermeable, the corrosion, the carbonation process cannot progress. It has to be partially saturated, not fully saturated. So, impervious concrete is very important, and of course, alkalinity of concrete is important. So, this would actually reduce down the carbonation process. Now, remember, this carbonation process per se is not a problem. Okay, it can cause some error in non-destructive testing, but forms a hard mass, it is a strong mass, and again it can actually cause a little bit of shrinkage in some cases, but it does not create any problem otherwise, but it can lead to process of corrosion initiation. Now, let me summarize this here today, because the processes would continue. We will discuss the carbonation process, its protection a little bit, then look into chloride ingress and ingress of chloride ingress and rebar corrosion process together with alkali aggregate reaction and frost action in the next process. We will overall summarize the whole process together in the next class. So, what we have looked today? We have looked into what we mean by durability, definitions of service life, then we have looked into what are the possible processes through which actually corrosion, deterioration of concrete takes place. Some processes we have tried to look into, the rest of the processes then we will look in the next class. Thank you.